Okay, welcome back. This is 3.1, Solve Quadratics by the Square Root Method. We're going to have two learning goals for this lesson. The first learning goal is to solve quadratics by using the square root method. And the second one is to leverage x-intercepts to solve word problems. Now, the second learning goal here, we're only going to talk about a little bit because I want you to see how this method will benefit us in a contextual problem. So let's start with the math talk. Can we solve for x when there is an x squared? Okay, and I bring up this point because on the left here, for x plus 3 is equal to 12, if I told you to solve for x, you would pretty much know what to do, right? Minus 3, x is equal to 9, right? To solve for a variable means to get the variable by itself. But when you look at the right, you have f of x is equal to x squared plus x plus 11. And if I ask you that same question to solve for x, well, how do you do that, right? Well, for starters, we know f of x is the same thing as y. And so this could be read as y is equal to x squared plus x plus 11. Okay, maybe we minus the 11, right? Like how do, we got to get everything over and left with x on one side. So we would have y minus 11 equals x squared plus x. And here's where the problem arises. How do you get just an x when you have an x squared and an x that cannot be simplified, right? I cannot add these together. So we know that if we have an x squared, we can take the square root. Okay, so let's try and get x squared by itself and take the square root. Okay, so we have y minus x minus 11 equals x squared. So we take the square root and the square root, and we're left with x is equal to the square root of y minus x minus 11. I hope you're seeing how ridiculous this is, okay? But I want to bring this point is that we cannot solve quadratics the same way we would solve a linear function, simply because of this x squared and this x, okay? So we're going to dive into one method this lesson, and then the rest of this unit is going to be all about this scenario. How can we solve for x with a quadratic? Okay. And just to point out another thing, right? You have variables in your answers. I mean, how ridiculous is that? You're going to say x is equal to, and there's an x in your answer. Kind of absurd, okay? So let's see how we would actually do this, all right? So the solve by square root method is the process of solving a quadratic equation by taking the square root of both sides, okay? Now, in order to do this, we need the perfect situation. And what I mean by that is that your b value must be 0, okay? Notice how in this quadratic, we don't even see a single x, okay? It's an x squared minus 144. That x being gone allows us to square root both sides to get rid of it and end up with just an x. And the other thing, is the other issue we saw on this previous page is that we had a y, right? Because this is y equals. Well, here, we're going to make y equal to 0, okay? And if we do that, we're solving for the x-intercept, right? So we're, in this perfect situation, we're able to get rid of those other variables so that we can use the square root method, okay? Now, if you are given a quadratic like this, a trinomial that does have an x squared and x, know that you will not be able to use this method, but there are other methods like factoring in the quadratic formula where you can do that, okay? So let's start this off. We would make this 0 is equal to x squared minus 144, and now we solve for x. You add 144 to both sides. This cancels. You have 144 is equal to x squared, which let's write it the other way. I always like the variable on the left. And then you square root both sides. Square root, and you get x is equal to plus or minus 12. And you need to include the plus and the minus now, because now we're talking about x-intercepts. You just found the place where your graph crosses the x-axis, but it's not one place. It's 12, 0, and it's negative 12, 0, which is a very important distinction. If you forget the plus and minus and you think there's only one when there's two, okay? All right, let's dive into some easy examples that look a little similar, some a little bit harder, a little bit longer, and see kind of the wide array of problems that we could get for this. And then we're going to sketch a graph and see what they would look like. Okay, keyword on the sketch. It's not going to be perfect, but I want you to kind of get a general idea of what these would look like graphed. Okay, so again, your process is make your y 0 because you're solving for the x-intercept. And because we don't have that simple bx term, meaning b is 0, we can just solve for x. So get x by itself. You have x squared is equal to 36. At this point and this point only, where you have just the x squared alone, is when you can square root both sides. And you get x is equal to plus or minus 6. Now, that means your x-intercepts is at 6, 0 and negative 6, 0. So if I were to just sketch a graph of what this would look like, okay, it would be, let's call this 6, 0. So that'll be 6, 0. And we'll call this negative 6, 0. Okay. We know our graph is going to kind of look like this, right? It's going up because our a value is positive, all right? And if you think kind of back to the parent function here, we know there's a minus 36 here, and it hasn't moved left or right at all because there is no h or there's no bx term. So we can even off the bat say that this is 0, negative 36, which may not always be so clear, but a lot of times it is. Okay. Now I want you to see this because we're finding a very significant place. We're finding where our graph crosses the x-axis, which is very important. All right. Now let's do the one on the right. It's a little bit longer. We make y 0, just like we did before. And then we solve for, in this case, a, but it's really all x, right? Okay, first thing you're going to want to do here is get rid of your k value because this is in vertex form. So I'm going to minus 27 to both sides. I'm going to get negative 27 is equal to negative 3 times a plus 2 squared. At this point, you would divide your a, well, not the a variable, but the a for the vertex form. We divide by the negative 3. We're trying to get everything down to just, the parentheses squared here. Okay, so that would cancel. Negative 27 divided by negative 3 is positive 9. And so we get 9 is equal to a plus 2 squared. Now that we got rid of everything around this squared, we can take the square root of both sides. Okay, so the square root cancels the square. And so you're just left with the a plus 2. And I'm going to flip this in the same step. We're left with a plus 2 is equal to the square root of 9 is plus or minus 3, which means you have two equations here, really, but we're going to leave it as the same. So I'm going to minus 2 to both sides. And this is equal to a is equal to plus or minus 3 minus 2. So a is equal to, and we do them both. Let's do the plus 3 minus 2, which is 1. And then let's do the negative 3 minus 2, which is negative 5. So you have 1, 0 and negative 5, 0. Okay. Now, in this case, it's not always clear. It's not always clear what the vertex is going to be. In that previous one, it was clear. And kind of in this one, we can read the vertex because it's in vertex form, but we're not always going to be able to find it. Okay, so let's not worry too much about the vertex. Let's just worry about seeing kind of the general picture here. So negative 5, we'll call it right here. Positive 1 is here. And if you think about it, it has to split the distance. So your vertex is going to be somewhere in between. Okay. Now, again, I know this one is in vertex form. We can find it, but not all of them. All right. Okay. So the general goal for square root method, set your y equal to 0 so you can solve for the x-intercept. Your b is equal to 0 so you don't even have that x term, okay? And then you want to get your x squared by itself so that you can take the square root of both sides, okay? All right. Now, solving quadratics by the square root, okay? You do. This is for you to do. Give it a try, and then we'll come back together and go over it. Okay, hopefully you gave this a try. Hopefully you set this equal to 0 So you get 0 is equal to 2x squared minus, oh, not 25, 50. You add the 50 to both sides. You get 50 is equal to 2x squared. You divide the 2. You get x squared is equal to 25. Notice how I flipped, right? Then you take the square root of square root, and you get x is equal to plus or minus 5, making your x-intercept 5, 0, and negative 5, 0, and then sketch it, right? So we have positive 5 and negative 5, so it must be going up, okay? And it will look something like that, all right? Now, on your assignment, you will be sketching them, okay? Because I really want you to keep thinking about what you just solved for, all right? Now, let's just take a little brief look around here, okay? On this page, I said that your b must be 0 in order to use this method, which is a half-truth, okay? And what I mean by half-truth is that in this problem here, x squared minus 144, b is 0. In this vertex form, b is not necessarily equal to 0, but we still don't have a b value because it's in vertex form. And when it's in vertex form, you don't see that term. So this is still okay to do, but it doesn't necessarily mean b is equal to 0 when it's in vertex form. Okay, so it's kind of a half-truth, all right? All right, we got to review before we start doing some more of the advanced problems. And this is something you should have seen in Algebra 1, but if you didn't, that's okay. It's called the factor tree method. It's when you're given a square root that doesn't work out so easily, right? Think back to these problems. Square root of 25 was 5, easy day, right? Square root of 36, plus or minus 6, right? Easy day. What happens when you square root of 75? You don't get just a number. So what you want to do is called the prime factorization. You want to break this down into all of its primes. Prime numbers are numbers, oh, that's an R. Prime numbers are numbers that can be divided by themselves and 1 only. So 1 is a prime, 2 is a prime, 3 is a prime, 4 is not, because 4 can be divided by 1, 2, and 4, all right? Only 1 in itself to make it a prime. 5 is a prime, 6 is not, 7 is a prime, 8 is not, 9 is not, 10 is not, 11 is a prime because it can only be divided by 11 and 1. So we're generally going to try and break these numbers down into their prime factors or into their perfect roots, okay? The way we do this with the factor tree method is break it down. So 75, what times what is 75? Well, I can see that 25 times 3 is 75. 3 being a prime factor, okay? So I know that's going to have to stay inside the square root. If I look at the 25, well, we know what the square root of 25 is, right? The square root of 25 is 5 because it's 5 times 5. So we're able to pull these out. So our answer would be 5 times the square root of 3, really plus or minus 5 times the square root of 3, right? Because there could be the plus version and the negative version. Now, you might have done this differently. I see that 15 can also go into 75. So let's do it again. 15 times 5. Well, 5 is a prime number. 15 is not, and 15 is not a perfect root, so we can't just pull it out. We get 3 times 5. So our prime factorization is 3 times 5 times 5. Notice how, again, we ended up with 2 5s that we can pull out. So we get, again, 5 times the square root of 3, plus or minus 5 times the square root of 3. It will be faster if you try to do what we did here, which is maybe you try and choose one of your factors to be something that can be square rooted, okay? But if not, you break it down to all the prime numbers, you pull out your doubles, okay? All right, let's do the square root of negative 32, right? And remember, this is where we start to get imaginary numbers. They're not going away. So I'm going to break this down, and I'm going to forget about the negative for a second. I'm just going to deal with the positives. I'm going to go 16 times 2. Well, 2 is a prime, and the square root of 16 is 4, so I know that this would be 4 times the square root of 2. However, it's a negative 32. So when you pull that out, that 4, it's going to really be a 4i. So it'll be 4i times the square root of 2, plus or minus. okay? Now, let's do that one again, but let's do it with different numbers. Let's do 8 times 4. 8 times 4 is 32. Now, I know 4 is a perfect square, so I could pull that out, but I also could look at it this way. 2 times 4 gives me 8, right? I have duplicate 4s, so I can pull those out as 1. I leave my prime factor inside, and because 32 is a negative, 4i times the square root of 2, okay? Now let's do square root of negative 24. Okay, square root of negative 24, break it down. Again, I look for my perfect roots, right? So 4 can easily have the square root taken of it, times 6. Now I know 6 can be broken down into 2 times 3, okay? But both of those are prime numbers, and there won't be any more duplicates, because when I take the square root of 4, I get 2. So I need to multiply those primes back together and get 2 times the square root of 6, okay? Now it was a negative 24, so I ends up in my answer. So plus or minus 2i times the square root of 6. I know 6 is not a prime, but when you end up with 2 primes that aren't duplicates, you can't break them down any further. They don't get pulled out, so they just get multiplied back together, okay? Now obviously, this could be really difficult if this is the first time that you've seen it. If it's not, then it's probably clicking. In Algebra 1, I would teach this as a full lesson almost, okay? So if you're struggling with this part, you might want to try, go look up a couple problems and practice it a little bit. All right, so now we're ready for kind of the harder problems here, okay? The problems that don't work out so easily. So we're going to do all the same steps. We set this equal to 0. We get 0 is equal to 10 times x minus 7 squared minus 440. We add the 440 to each side. This cancels. We have 440 is equal to 10 times x minus 7 squared divided by, why am I writing 2? Divided by 10. This cancels. 440 divided by 10 is 44, which is now equal to x minus 7 squared. We're going to take the square root of both sides, because now we're at that point where it's just parentheses squared. And this is where we run into that issue that we just prepared for, okay? So the square root of 44, we need to do the factor tree. So I'm going to do that in green. I'm just going to write it off, kind of to the side separately. I know that 4 times 11 gives me 44. 11 is a prime number. The square root of 4 gives me 2. So this is the same thing as plus or minus 2 times the square root of 11, okay? So we get, I'm going to flip this. So it's going to be x minus 7 is equal to plus or minus 2 times the square root of 11, okay? Then I need to add the 7, and I get x is equal to plus or minus 2 times the square root of 11 plus 7, okay? Now the 7 and the 2 times the square root of 11 cannot be simplified, and they cannot be simplified because, if you try to go and say 2 plus 7 is 9 times the square root of 11, that's all messed up because 7 was never being multiplied with the square root of 11. Now, if you had a calculator, you could simplify this further, but we're going to leave this, and that would be your answer, okay? Now, if you sketch this, well, it's a little bit harder to sketch here, okay? Because you see that we are, we have plus 2 times the square root of 11 plus 7, and negative 2 times the square root of 11 plus 7, and you got to be asking yourself, where is that number? Where is negative 2 times the square root of 11 plus 7? They're not always going to be this hard to figure out, but if you think about it, negative 2 times the square root of 11 is not going to be a big, a very big number, right? It's not going to be bigger than 7 if I multiply those together, because think about this, the square root of 9 is 3. Let me zoom in on this. The square root of 16 is 4. So the square root of 11 has to be between the numbers of 3 and 4, right? So maybe I get close to 7. Maybe, with doing 2 times the square root of 11. But that negative version won't be enough to be bigger than 7, okay? So we know it's going to be still on the positive side. So negative 2 times the square root of 11 plus 7, and then something like 2 times the square root of 11 plus 7. That's a hard one, okay? And I don't think you're going to see too many that hard. I think normally you'll see it like this. Normally you'll get like a plus or minus 2 times the square root of 3 as your final answer. And here, you're -1, and you'll have a -1 and a +1. So -2 times the square root of 3 over here, and 2 times the square root of 3 over here. And then, you would draw like this, okay? All right. Let me just go back quickly and check a couple things. Ah ha ha ha. Ah ha ha ha. You guys thought you were going to leave some nasty feedback about my errors, weren't you? This sketch was incorrect. The sketch was incorrect because it had a negative a value. So it was -5 and 1, and it would have been upside down. Sorry, the current problem just made me think about that. For all of you who are preparing your trolls on the feedback, not today is my response to you. Maybe next lesson though, all right? Okay, so we get 0 is equal to, sorry, we're gonna move on to the next problem. That was a pretty tough one, okay? Definitely one of the harder ones. So 0 is equal to x minus 8 squared plus 16. We're gonna minus 16 to both sides. We get -16 is equal to x minus 8 squared. We square root both sides, right? We're going to get that negative, that imaginary number. That's totally okay. We end up with x minus 8 is equal to 4i. The square root of 16 is 4. The square root of -16 is 4i. Plus or minus 4i. So we're going to add 8 to both sides. And then we're going to get our answer. X is equal to plus or minus 4i plus 8. Okay? Now you got to remember here, imaginary numbers means that it never crosses the axis. Okay? And I have a positive a value, so I know it's going up. So if it's going up, it has to be above somewhere if I sketch it. Okay? And the reason why it has to be above is because if it was below the x-axis, it would cross the x-axis if it was going up, right? So we don't actually have a point that we're going to pick out and go, oh, that's where positive 4i plus 8 is, or that's where negative 4i plus 8 is, because they don't ever cross, okay? So that one's going to be tricky. If you had a negative a value here and you have an x-intercept that says there's imaginary numbers, then it would all need to be below the x-axis facing down, okay? All right, those were tough. You will have stuff like this on your assignment, these tougher ones, so make sure you're ready for these. In fact, what on earth is that? Okay. Let's do something else here. I don't even know what I was trying to do. Let's just cross this out. Dang. Okay. Let's just do that one. Let's get rid of that equals 21. I don't know how that made that in there. And do this. Take a couple, pause the video, give it a try. I'll go over it. All right, hopefully you got that. You make this equal to 0. Solve for m. Oh man, this problem's really messed up. It says C and D. And here I was thinking that the trolls were not going to come out. So we end up with -7 is equal to -3 m squared. We're going to divide -3, divide -3. You should get 7 over 3, because the negatives cancel out, is equal to m squared. You take the square root of both sides. You get m is equal to plus or minus the square root of 7 over 3. So if you go to sketch this, somewhere over here is negative square root of 7 over 3. And somewhere over here is positive square root of 7 over 3, okay? And we know that it's going down because it has an a value that's negative. So that means its vertex must be somewhere up top, okay? We just want you sketching in this lesson because we want you thinking about what this means, where it looks, even though we're really focused on solving instead of graphing right now, okay? Now, I think I intended a little bit different of a problem here, so I might supplement with a little bit of a what-if section, okay? But I do have another math talk for you guys about the x-intercepts and why we care looking for these so much. In previous lessons, right, if, here we go, I got a football here, Lovely artwork. And I throw this. Okay. Oh yeah, that's excellent. Excellent throw. Okay. And the ground is, let's go like this. Here's the ground, which is kind of like your x-axis, right? Now notice how I'm going to have to just go like this, even though that's not where the ball was, all right, to kind of complete that quadratic. In previous lessons, you cared so much about this high point, right? The vertex. And we asked a lot of questions related to that. Could this jump over that? Could this, what was the high score? We were all about highest or lowest value because that's what we knew with the quadratic at that point. But when we bring in the conversation of x-intercepts, okay, we're now talking about these points, okay? Here being the place where the ball lands, right? Here technically being a point that never existed because the ball never actually went there, right? Because the ball is in my hand right here. But we would get a close kind of distance here, right? So the distance between these points could mean a lot of stuff. Now, we might have to take into account of this position a little bit differently and subtract some stuff off of that distance, okay? But when we start thinking of x-intercepts, it's starting to paint a different story. It's starting to tell you where things land, where things start, and the distance between those 2 points. Okay, so we're starting to come full circle on everything that we can start to pull out and the types of problems that we can do with this. Okay, if you're a daredevil and you want to jump over the Grand Canyon, well, you want to know if you hit a certain arc, am I going to go a certain distance and clear that point? Okay, so we're learning, think of your word problems in these lessons and start to think about what the x-intercept tells you when you're solving them. We're no longer thinking about the maximum point. We're thinking about our x-intercepts, and that's what you've been solving for this whole time. Okay, now a quick little, what if section. All right, if you have something like this, x squared equals, let's go 16 over 9, which you can't really simplify 16 over 9, and you take the square root like this and this, and you get x is equal to, plus or minus the square root of 16 over 9. You got to know in this case that you can simplify that further, that you can apply that square root to the top and the bottom. You can do the square root of 16 over the square root of 9, which is equal to 4 over 3, plus or minus. You can take another step and simplify that just a little bit further, okay? All right, everybody, that was a long video. I hope you got something out of it. I hope the thing was actually recording because, believe it or not, I've done entire videos where the audio wasn't even recording. So good luck, and please leave some feedback. I'll see you guys in class.